Alright guys, welcome to Chemical Kinetics. This is going to be the chapter 14 in your textbook, so make sure you have your chapter 14 open and ready to go in your text and your guided notes. Here we go. Kinetics. Alright, this is a new topic for everybody. You've never been exposed to this ever before. And this is one of the more interesting sections in AP Chemistry because you get to actually talk about what physically happens in a chemical reaction to make the particles recombine into something totally different. It mostly is the study of the rate at which a reaction can occur. So we talk a lot about how physically these reactions can go and how they prefer to go and how they can sometimes be limited by certain factors in the reaction and how they can proceed faster by certain factors in the reaction. So it's kind of a study of how fast and how slow a reaction can go based off of various things that can happen. It says, besides information about the speed at which a reaction occurs, kinetics also sheds light on the reaction mechanism. That would be exactly how the reaction can occur. So it's kind of neat. This is getting pretty deep into AP Chemistry, and I gotta say that I'm really proud of all of you guys for sticking with it, because up until this point, yeah, I showed you a few new things in thermochemistry, but kinetics is brand new. And like I expressed last class, I really need you guys to start reading the chapters. And I'm starting to feel like these podcasts are becoming less and less valuable to you, whereas the book should be your primary resource. This is just a backup. So anyway, let's keep going. So here are some factors that can affect a reaction rate, how fast the reaction goes. Obviously, the physical state of the reactants makes a big difference. I showed you last class two solid ionic substances that when I mixed together, because they were so endothermic, the solution turned into kind of a slushy type thing, and the outside of the container actually frosted over. So could you imagine if I had made the reaction into a solution first, like both of the reactants, if I made them like into an aqueous solution first? That would have been a much faster reaction than what you guys saw in class. So solid, it would be kind of like if I take two metals and try to rub them together and somehow make an alloy. Like, that's not going to happen, right? You would expect to have to heat it up into a liquid. So it says, in order to react, molecules must come in contact with one another. And in order for the reaction to proceed faster, the more homogeneous the mixture of the reactants is, in other words, the more it looks the same throughout, then the faster the molecules can react with one another. So the more heterogeneous the mixture looks, then the slower the reaction will happen. So you want the molecules to be thoroughly mixed with one another to readily enable a reaction to go in the first place. And then another factor that obviously will affect the reaction rate is the concentration of the reactants. So here you see two pictures. They're both steel wool. The picture on the left is being burned. The steel wool is being burned, and it looks like it's just being burned in air, like regular air. I don't know if I told you this before, but oxygen, which is what is required for a fire to go, for things to burn, is not really very concentrated in your atmosphere. So in the reaction on the right side, in this picture on the right, what they did is they dunked the slightly burning, steel wool into a flask that is rich in oxygen gas. And you can see that it makes a huge difference in the reaction rate here. So it says, as the concentration of reactants increases, so does the likelihood that reactant molecules will collide with one another. And that's the ultimate goal of a chemical reaction, is to get the two molecules to hit each other just right so that the reaction will proceed. Obviously, the other factor that can affect reaction rate is the temperature. The hotter you go, the more kinetic energy the molecules have, And the more kinetic energy they have, the more likely they will collide with one another with more force. So the higher the temperature is, the particles start moving faster. They collide with each other more often. And if we can get those particles to collide with one another with enough energy, in other words, with enough oomph, then the reaction will go faster. And then this is something that we didn't really talk about, but I can definitely show you a really quick demonstration next class. The presence of a catalyst. So I don't know if you guys are familiar with hydrogen peroxide. Hydrogen peroxide naturally decomposes by itself, but it's a rather slow decomposition reaction unless you add a catalyst. So the formula for hydrogen peroxide is H2O2. It kind of looks like water, but with an extra oxygen on there. And it's kind of an unstable configuration for H2O2. It doesn't like to go like this, so it naturally, on its own, will decompose into the elements that we have here. So H2O is one of the products. Now I challenge you to try to think of what the other product would be, because water is the compound, and I'll tell you that the other product is a element. But the question is, which element do you think would more readily come off of the hydrogen peroxide? Do you think oxygen would come off, or do you think hydrogen would come off? The correct answer is oxygen. Hydrogen is extremely reactive, and oxygen a lot less so, and it's a lot easier for the oxygen to be removed than for the hydrogen to be removed. Think about electronegativity. Oxygen is a pretty strong electronegative element in this particular decomposition reaction, and so it's more greedy for the electrons. So hydrogen can be popped off pretty easily, but oxygen is more greedy for the electrons ultimately, and so it'll balance itself out. So anyway, this is not balanced, but one of the things that we could do to speed up the decomposition of hydrogen peroxide is by the use of introducing a catalyst. And usually the way that we introduce a catalyst is by writing it over the top of the arrow. Potassium iodide happens to make this particular reaction speed up huge amount. Hydrogen peroxide, the type that you guys get when you go to the drugstore, versus the hydrogen peroxide that can be used for, say, rocket fuel. Believe it or not, yes, hydrogen peroxide can be used for rocket fuel, especially when you approach anything basically over, I would say, 80% composition is extremely reactive. Hydrogen peroxide is very unstable, and that's why you always buy hydrogen peroxide in those dark containers. The dark container prevents it from being exposed to light, and light will make hydrogen peroxide decompose into water and oxygen gas. So anyway, the hydrogen peroxide that I have is not the same stuff that you buy in the grocery store. I think the stuff in the grocery store is something like 30% hydrogen peroxide. I think I've got 60% or 70%, something like that. So anyway, we'll have to check that out maybe next class. And anyway, a catalyst, basically all it needs to do is to speed up the reaction, and it changes the mechanism. The mechanism is the driving force behind a chemical reaction. But the catalyst, all it will do is speed up the reaction without actually changing itself or the products that are formed. So in other words, it's just kind of there to assist the atoms in colliding properly with one another. So it's a bystander. It's not a reactant, it's not a product, it's just kind of in there. How it is at the beginning is how it is at the end. There is no chemical change for this catalyst, so they just help the reaction go faster. Click. It says catalysts are not consumed during the course of the reaction. So, all right. So here's a general overview of all the different things that can change the reaction rate. Number one, the physical state. Gases react a lot quicker than solids and liquids. Liquids more so than solids. concentration of the reactants, temperature of the reaction, presence of a catalyst, and then I threw this one in here, number 5, surface area of a solid or liquid. Basically, if you crush up, think of an Alka-Seltzer pellet. You can throw a whole Alka-Seltzer pellet into water, or you can crush it up and throw it into water. And which one do you think will react faster? Anything you crush up, chop up, or slice up into a reaction in chemistry makes the reaction proceed a lot faster. So surface area, basically chopping things up. All right, time to start talking about the math. Don't be scared. Here we go. First, reaction rate technical definition is the change in concentration or molarity of reactants or products per unit of time. So, take for consideration, nitrogen gas can, through some pretty technical, mechanism, through this pretty interesting mechanism, nitrogen dioxide can form dinitrogen tetraoxide gas. It's a pretty interesting mechanism. So the expression for the reaction rate itself would be for N2O2. I want you to notice that N2O2 is in the products for this particular reaction. Would basically be delta, or change in molarity, of N2O4 over delta T. And remember that whenever you see that delta sign, it's usually final minus initial. The final state minus the initial state. And at this point, I just wanted to also express one little thing. I concentrated on the formation of the product in this expression right here. That is a reaction rate expression for this particular product. But what if I challenge you to do a reaction rate expression for the reactant? Here's the difference. You're forming products. So your reaction rate here will be a positive sign. But what about if you're talking about a reactant? Reactants, their concentration should go down as the reaction proceeds from the beginning to the end of the reaction. So with this one, it's going to be going away, right? So you should make a negative sign. Change in concentration, NO2, over delta T. And also, we'll talk about what this coefficient will do to this reaction rate expression. I don't want to confuse you too much, but basically this sucker is going to be losing its concentration twice as fast as the product, because it's a 2-to-1 mole ratio. So mole ratio is definitely, remember concentration and stoichiometry. Basically, the reactant is going away twice as fast as you are forming your product. We'll get to that later. Okay, so going back to the general, what a reaction rate does, it says rates of reactions can be determined by monitoring the change in concentration of either reactants or products as a function of time. So as you can see, this would be kind of like the reaction that I was just using as an example. What if this was all NO2 gas? And it naturally on its own through time will steadily start making the dinitrogen tetraoxide. And then finally, if you give it lots of time, you get a lot more dinitrogen tetraoxide. So you see the mole A, mole B, and then it changes as it goes down. Notice A, you started with 1 mole, and then as the reaction proceeds, you get less and less. So the concentration of A is going down with time. Now notice with B, you started with 0 moles of B, but as the reaction continues from the beginning to the end, you slowly increase the concentration of mole B. Here's another example. Here's the reaction written up here in red. It says, in this reaction, the concentration of butyl chloride, C4H9Cl, notice where is that? That's on the reactant side. So the molarity of this was measured versus time. So as time went by, it looks like the concentration or molarity decreased with time. And then notice they put a very long time over here until it was all completely gone. So this is a function of molarity versus time. Now in this particular slide, we're doing something different. We're measuring something called the average rate. It says the average rate of the reaction over each interval is the change in concentration divided by the change in time. So overall average rate would be any change in the reactant here. This is called, I can't remember what they just called it, over a specific amount of time. So what they did is they calculated the average rate between two time intervals, and they did it consistently for each time interval given over here. So change in molarity divided by change in time. And remember, it's final molarity minus initial molarity. These should be negatives. Make sure I'm doing this. Yeah, these should be negatives, I think. Anyway, keep going. Alright, so note that the average rate decreases as the reaction proceeds. So it started off really fast and vigorous, and then as we go down, the reaction got a lot slower. This makes sense because we talked about how concentration will affect the rate of a reaction. So what they did is it says this is because as the reaction goes forward, there's fewer collisions. That makes sense. So once it makes the products, it's stabilizing. This is a spontaneous reaction, and so we're trying to lower the overall energy to make it more stable. So these must have high energy, these must have low energy. It's a spontaneous thing going on here. And it looks like the reaction is slowing down, slowing down, slowing down. So here is a graph of that particular molarity versus time. And you'll see, as you can see, the slope. You see the slope at each individual point gets lower and lower and lower. The initial reaction rate, you see the slope right here, this line that they kind of drew? The initial reaction rate is really fast. But then as the reaction proceeds, if you start doing some slopes down here, the slope is much lower. This is nice and steep, this line right here. And this line right here is much lower. Alright, so now time for a little bit of some definitions. We've got this definition right here. It says instantaneous reaction rate. And this says instantaneous reaction rate. These are at two different times. This is time is equal to 0, and this is time is equal to 600 seconds. You need to note something here. An instantaneous reaction rate would not require 2 points on this graph. That's kind of scary. Have you ever heard of something called the tangent of the line? Tangent of the line basically takes the two time, like you know how usually on a slope of a line you need 2 points and it's rise over run? Well, there isn't 2 points. There isn't 2 points to compare. Instantaneous reaction rate would be a single tiny little spot on this line. And for those of you math whizzes, there's this word called tangent of the line. I would strongly recommend that if you've never heard of the tangent of a line, that you should probably look it up on Google. Maybe I'll make that one of your little resources that I can email to all of you. Tangent of the line. Okay, it says the slope of a line tangent to the curve at any single point, I want to make an emphasis here of a single tiny point, is called the instantaneous rate at that time. It says all reactions slow down over time. Therefore, the best indicator of the reaction, the best indicator of the rate of a reaction is the instantaneous rate near the beginning of the reaction. It says in this reaction, the ratio of C4H9Cl to C4H9OH, which is your product, so reactant to product, is 1:1. So check out your rates here. It says thus, the rate of disappearance of C4H9Cl is the same as the rate of appearance of C4H9OH, with one very important difference. since C4H9Cl is disappearing over time, in other words, it's a reactant, look at this right here. Do you see that? It's a negative because it's going away. The concentration is going down, final minus initial. And then over here, because we're forming C4H9OH, we're making it, this would be a positive expression. So negative for reactants, positive for your products. This stuff is going away, this stuff is being formed. So I wanted to kind of go over a little bit of the 3 different types of reaction rates that you can that we talk about with kinetics. The first one would be average reaction rate. This is the rate of change of concentration over a specific time period. So we can make those small time periods, or we can do like the whole reaction rate, the whole thing. But typically what we like to do is take small chunks. So if you look back at the initial reaction here, you see these time intervals, the dots? If I took the difference between one dot and another dot, that would give me the average, which is what they calculated here. You see these little time intervals right here? So for each of their measurements that they took in molarity in these time intervals, they can calculate something called average rate, which is expressed as molarity per second. So coming back to here, let me go over. So that's average reaction rate over a specific time period. Then there's this thing called instantaneous reaction rate. That's where it's like a single tiny little spot on the line. It's no longer 2 points on this curve, right? Because it's not really a line, it's a curve. It's not between 2 points. It's like taking those 2 points and squeezing them as close together as possible, so you have a really small infinitesimal time interval. Basically no time interval, it's just right there, instantaneous. So I know some of you have never heard of this, but that would be the slope of the tangent to the plot. And that is something that, thank God, we don't have to calculate. It's not really something that they have you calculate in AP Chemistry. They usually ask for things called the average reaction rate. But they need you to understand what the instantaneous reaction rate would be looking like, or what it really means. And then finally, the third definition here is the initial reaction rate. Did you notice that for the initial reaction rate back here on the slope, did you notice that the line that is formed for the instantaneous reaction rate right here, did you notice that the line being formed is really close to the actual line? You see this that I'm drawing right here? Do you see how between these periods, between right here and right here, it looks like the line is pretty darn close to the tangent is really darn close to the actual line being formed. And that's why they like to say that the initial reaction rate is a really close indicator for the true overall reaction rate. So come back to here, this initial reaction rate that they're talking about is a really good indicator at the very beginning of the reaction of the true reaction rate at the beginning. And you know that it slows down over time. But anyway, here's an example. It says, consider this very simple reaction. You've got A making something new, B. And it says, see data from reaction in question 15 on page 616 of your textbook. So this is in your practice problems on this chapter on page 616. It says, what is the average reaction rate over the time interval t is equal to 10 minutes to t is equal to 20 minutes? So notice I'm saying average reaction rate, and it's giving you a very specific time interval. And also, one very important thing, it says, notice that the reaction has all ones in the front of the coefficients, because that's going to make this a lot easier. So your answer would just be the molarity final minus the molarity initial over the change of time. So your final molarity, the molarity at, I can't remember what time interval that was, at 20 minutes, was 0.042. So it looks like the molarity was lower than the initial molarity of that time interval, which was 0.051. And then we divided it by 10 minutes. That was the time interval. And it says, notice it's negative because the reactant A is going away. It says, notice this is average reaction rate over specific space of time. And I also want to talk a little bit about the units for this reaction rate expression, because basically what these are concentrations, which is the same as molarity. So this would be moles per liter per second. So it's moles per liter, because moles per liter is molarity, per second, and in this case, I'm sorry, it's not per second, it's per minute. Okay, so your reaction rate will look very similar to this. It will either be moles per liter minute or moles per liter second, and if you're really, really lucky, you might get moles per liter per millisecond, which is really fast. And some reactions really are that fast. It's pretty instantaneous on some of them. All right. I wanted to give you a little bit more exposure on looking at these reaction rates. So here's yet another example, and I color-coded the lines this time. So the blue line is the average rate of reaction between time 0 and time 1,000 seconds. So notice these average reaction rates can be very long periods of time, or we can shorten them up a little bit if you have specific spots. You see how there's a dot right there and there's a dot right there. These are where we probably took molarity measurements over time. Or you can just do the whole dang thing from beginning to end when there's 0 molarity left. You see that? All right, the red line is something called the slope of the tangent. So as we make these points in between smaller and smaller and smaller and smaller and bring them together, the slope of the tangent is found. And so this line right here was found by a single point on the line. And then finally the green line, remember how I talked about the green line matching the initial reaction rate really close. And that's why people like to talk about the initial reaction rate, because it's really accurate. Okay, from the previous slide, okay, looking at that graph, it says the average rate of reaction between, say, time 0 to 1,000, the blue line, that really big blue line, okay, is 0 molarity minus 0.75 molarity. So let's go back and look. You'll notice that the final molarity down here on the line, come across, is 0. This is the 0 molarity, the final molarity. The initial molarity looks like it started around 0.75 in between this 0.7 and 0.8. So that's where we got the 0 minus 0.75. Will this be positive or negative? Think about that. Because it's going to be negative. This must be the reactant. And then it's divided by the final time minus the initial time. If you do your math very carefully, you will get a negative 7.5 times 10 to the negative 4 molarity, or moles per liter second. See there? What is this? Moles. Whoop, sorry. Hold on. MM per second? No. Okay, I wish I could fix that. Get rid of that lowercase m. I have no idea what that is. Anyway, it says, but the instantaneous rate of the reaction at t 400 seconds, or the slope of the tangent, the red line, at t 400, is 0 molarity minus 0.18 molarity divided by 600 seconds minus 200 seconds, which is equal to negative, please notice that there is a negative there, it just didn't follow, negative 4.5 times 10 to the negative 4 molarity per second, or moles per second. Here, did that again, lowercase m, capital M. All right, finally it says, what if there isn't a 1-to-1 mole ratio? Because remember, I told you that concentration definitely has something to do with the rate of a reaction. Well, for the rate of a reaction, you need to realize that sometimes you have reactants going away twice as fast as you make a product. Check out this example. This is that one that I was talking about, the nitrogen dioxide. When it hits itself just right, in other words, if the mechanism just hits each other perfectly, it can make dinitrogen tetroxide. So it says reaction rates are directly related to the reaction equation stoichiometry. So here's our reaction. It says that there is 2 moles NO2 are reacted when 1 mole N2O4 is produced. So let's look at this one a little closer. It says reaction rate. Here's your reaction up here in case you forgot. It says reaction rate in terms of appearance of the product. Okay, so here's your product. It is very simple. You see how there's a 1 in front of the, or there's no number there, but it's assumed to be a 1 on the coefficient. Very simple. Change in molarity over time. But reaction rate in terms of the disappearance of the reactant is a little different. It's going away, so it needs to be negative. And notice this. You see the 1/2? 1/2 change in molarity of NO2 over time. So this coefficient made the reaction rate go away in half. It says if something is being reacted, it's positive rate. If something is disappearing, it's negative rate. I think I pounded that into your head enough this time. So let's generalize then for the reaction rates. Let's pretend like we have this reaction here. You have a coefficient of lowercase a for A and a coefficient of lowercase b for B. So these are numbers and these are like the formulas, making a lowercase c for C and a lowercase d for D. So the lowercase letters are like coefficients. They can be like numbers, 1, 2, 3, 4, 5. This is what the reaction rate would look like. So A is a reactant, so it's negative. And if there's a coefficient in front of A, then we need to put that as a fraction under 1. And remember, it is negative. So 1 over A, change in concentration A over time, is equal to negative, because B is a reactant, negative 1 over lowercase b, change in B over time. And then notice your products. They're positive, there's no negative, because they're being formed. Pretty cool, huh? You need to know this one for sure. Now let's check this out as an example. Here's a reaction where 2 HI gas molecules, if they hit each other just right, they will naturally decompose into hydrogen gas and iodine gas. It says, what is the reaction rate expression for this reaction? So we're going to do each component separately. We're going to do this reactant, then this product, then this product. Starting with this one because it's kind of difficult. This is a reactant, so it's going away. We need to remember that there's a negative. We're going to put 1 over 2. The coefficient is a 2. If it was a 3, we'd put 3 on the bottom. Change in concentration HI, molarity, remember, divided by change in time. For hydrogen gas, there's no coefficient, so that one's easy. Just delta hydrogen gas over delta T. And here's your iodine. And that would be delta molarity of iodine over delta T. Remember, all these deltas are finals minus initials. And it says, of course, notice delta HI is negative because it's a reactant that's going away. All right, guys, we're going to stop for now. This takes you to the 3rd section of the chapter. I strongly recommend that you go back and look at all of the material that I've covered in the book by yourself and study. If you need to form a study group, there is an option coming up. I posted it on the wiki page for you. This next Friday, I think it's the 12th, if you would like to come in Friday after school, I would like to have an open study session with all of my AP Chemistry students. It needs to be serious, buckle down, get to work, no socialization kind of thing. But if you want it, if you want to come and be part of the group for that day, that's the day I'm going to offer to everybody. I'm starting to feel a lot of you guys slipping away because the material is starting to get hard. And the pace is not going to stop. If you are falling behind at this point, you need to remember that I'm maintaining the same pace as before, which means you're going to have to maintain my current pace and go back. I want you to also notice that on Infinite Campus, when we have an assignment that is due that day, I will put a yes or a no. Or I'm sorry, a yes or a missing. If it is missing, that means that your assignment is late. And late assignments, I'm getting real tired of grading them, late assignments are going to have a 25% dock. And then, if you still can't get it in within, say, like a week of when it was due, then we're going to have a serious conversation. I'm worried about you guys. You're starting to fall behind. Come talk to me. I need to see you guys more often, okay? It's not that I think you guys smell great, because you're starting to look a little ragged. All right? Remember to sleep. Remember to eat. I care about you, and I love you all. Take care.